All right, let's go ahead and get started. Thanks again for joining us today. This is the first Tech Tuesday session presented by Vic Myers Associates with our partner Data Physics. And today on our panel, we have three great resources from Data Physics. Our first and main presenter will be Raman Sridharan, and he's the product manager for vibration controllers at Data Physics. We also on the line have Alfred Johnson, the product manager for electrodynamic shakers at Data Physics Corporation, and Paul Hogue, the Western Regional Manager for test systems at Data Physics. Raman is one of the leaders at Data Physics for vibration controllers. He completed his master's thesis on the topic of fatigue damage during multi-axial vibration and has been with Data Physics for 9 years. Alfred Johnson has 33 years of experience in vibration testing and has been with Data Physics for 12 years. He's designed, assembled, serviced, and sold vibration test systems for Kimball Industries, Ling Electronics, Bond Engineering, and Data Physics. And Paul Hogue is also part of the Team Corporation. He's new to the NVT group, but comes with a lot of experience in commercial industrial technology sales. Thanks everyone for joining us. Again, my name is Ryan Christian, moderating today from Vic Myers Associates, field engineer in the Arizona territory. So at this time, I'd like to turn it over to Raman to begin the presentation.
All right, hi everyone. So as Ryan mentioned, I'm product manager for vibration controllers at Data Physics. And the topic of presentation today is major considerations for vibration tests of spacecraft and space electronics. So the agenda today, we're going to talk a little bit about satellite qualification, why and how satellite qualification tests are run, accelerometer sensor placement when you're testing a satellite, and then control and notch limit channels. And then we're going to jump into a safety system that was engineered by Data Physics and team, and talk about the vibration controller considerations and the system as a whole to prevent any catastrophic failure when testing a satellite or a launch vehicle. So the satellite qualification overview section, this is going to be an introductory section. So if you're familiar with satellite testing, then you probably are familiar with things in this section, but just to give those that aren't a overview. Obviously satellites are, once they're put into space or once they're put into service, they are not able to be serviced. So a failure or mechanical failure can result in a huge financial loss. There's no do-overs. Because of that, satellites are meticulously engineered and designed. They undergo more engineering than possibly any other devices that humans design and develop. In particular, finite element modeling is used extensively to model each component and then the total assembly of a satellite. And those finite element models, of course, the satellite's designed such in a way that if those finite element models are correct, the satellite should withstand its launch and go into service without any issues. But then the big problem is, how do you verify that your finite element models are accurate and are correct? So the only way to actually do that is to build a satellite and put it on a shaker and compare those results from the shaker test to your finite element modeling. And in that way you validate that the satellite does in fact meet your design specs. So the most common type of satellite test that's run on a shaker is a very fast sine sweep, usually at 4 octaves per minute, which excites all resonances in the satellite or in the test article. You usually use a fast sine sweep because you don't want to be dwelling at particular frequencies. You don't want to give the sinusoidal energy time to do some damage. You want to get through your sweep as quickly as possible. And you also want to excite every resonance. That's why you do a sine sweep and not a random test. So a lot of people do sine sweep testing. What's the big difference between testing a satellite and testing, a car or a truck. Well, the biggest difference is that the design cost of the test article and how fragile the test article is. Most of the electronic components, most of the components that go into a satellite are all custom designed, custom engineered for a specific purpose. So their design costs and manufacturing costs are extremely high. And there's obviously a lot of anxiety when you're putting this very expensive test article onto a shaker that's capable of, if something goes wrong, tearing it to pieces. So the picture on the right-hand side here is the James Webb Space Telescope, which is the most valuable test article ever put onto a shaker. So obviously, before they tested that test article, they went through a slew of tests, and we worked directly with NASA to develop a safety system to prevent any type of catastrophic failure. So the name of the game is risk mitigation when you're putting the satellite onto a shaker and shaking it. You want to design for the unexpected. Things you don't expect to happen. Well, just in case, the off chance that they do happen, you want to make sure that it doesn't actually damage the satellite while it's on the shaker. So I've got a couple quick videos here of the actual satellite being tested. This is an actual test of the James Webb Space Telescope when it was at NASA Goddard Space Flight Center in Maryland. So this is a sine excitation. I'm not sure how clear the video is going to come through on the web presentation, but you can see as it's being excited, the whole satellite is deforming and being excited at its resonances. So typically these tests are run in 3 axes. They'll test the satellite in one axis, then pick it up and rotate it, test it in another axis, and then test it in the 3rd axis. So this video has a screen grab, or this video has some video of all 3 axes. Is the 2 horizontal, and here's the vertical axis. So this test was the result of many months of preparation, and the test went off successfully. So I have one other video I want to show. This is from a couple years ago. This is the Orion service module being tested at NASA Plumbrook Station in Sandusky, Ohio. So this particular shaker table is actually a 6-degree freedom shaker table, but they run the exact same test. They test it in the X, they test it in the Y, they test it in the Z. Even though this table can move in 6-degree of freedom, they could do all 3 at one time. But the reason they designed this table for 6-degree of freedom, in spite of the fact they're just doing 1 degree of freedom at a time, is because now they don't have to actually pick the satellite up with a crane and rotate it to test the 2nd axis and the 3rd axis. And so again, why is that a big deal? Well, anytime you pick up the satellite with a crane, you're risking dropping it. And they have to mount it on the shaker once, and they can run all 3 tests. So even just that is a huge plus for a huge mitigation risk. Okay, so we're going to move into accelerometer and sensor placement. This is sort of still big picture, what you're trying to get out of your satellite test. So there's 2 different types of sensors, or 3 different types of sensors. The control sensors that are used to control the vibration on the table. The control sensors are usually placed on the slip plate or the head expander. These are sort of the input acceleration into the satellite. So the satellite's mounted on. You can see in this picture of the model of the Orion service module. The control accelerometers for this test were placed along the blue shaker head. So those are, and then the satellite's mounted to that, and your control accelerometers are placed around that. So that's sort of the input vibration that you are putting into the satellite. Typically, you run multiple control accelerometers, and you use them in an extremal control mode. So for example, if you've got one sensor that's reading half a G and the other one is reading 1G, the extremal mode would use whatever is highest as your control channel. So again, you're minimizing risk, right? You don't want to, if you're seeing half a G and 1G, you don't want to overtest. So whatever the highest vibration your control sensors pick up, you want that to be your control value. The other advantage of using multiple control accels is it prevents overtests due to anti-resonances. So these shaker tables that you mount the test article on are not entirely rigid. They can have some deformations, so you can have resonances, anti-resonances in your shaker table that can affect your test. And when you're running a test on a valuable test article, you want to prevent overtests. So multiple control accelerometers using extremal mode that prevents a resonance from taking over and damaging the satellite, and using multiple control accelerometers prevents overtest due to an anti-resonance, one of your control locations being at an anti-resonance or a node. That would not affect your test if you have multiple control accels. Right, and the last bullet point here is that control locations have to be chosen with the mode shapes of the slip table or head expander in mind. So you've got to look at your mode shapes, your head expander, look at your test frequency band. If you're going to excite a particular mode shape, you need to make sure your control accelerometers can detect that excitation and employ one of these control techniques to make sure you don't overtest your test article. All right, so the other types of sensors are the control sensors, which determine how hard you drive the shaker, used for your feedback control. The other sensors are measurement sensors and limit sensors. So the satellite obviously is composed of lots of substructures. Each have their own mode shapes, each have their own resonances. And since satellites are so meticulously designed, you can get predictions of those resonant frequencies and mode shapes out of finite element. And those finite element results are usually used to decide where you want to place your sensor. If you know a particular beam or plate on your test article is going to be resonating during your sine sweep, you want to put a sensor there so you can measure it. And so you can, if needed, you can limit the vibration there to prevent damage to the test article. I'll be talking about limiting in a couple more slides. And typically, for depending on the size of the test article, obviously, but you can have hundreds of sensors on the satellite to monitor all different locations, and a lot of those sensors can be connected, or often connected to a second analyzer system. You don't always want to clutter up your vibration controller with 100 or 500 channels and risk slowing it down. So typically satellite tests are run with an analyzer running in parallel that's monitoring hundreds of channels while the control loop is focused on your control and limit channels. So the limit and notching channels, sometimes limit and notching means the same thing. Basically, you've got this satellite made of all these subcomponents. Each of them has have different resonances when they're all built together and bolted down together. Any one of those parts can still resonate at its resonant frequencies, and if you aren't careful, if you let one of those substructures resonate too hard, that can cause damage to itself or other parts of the satellite. So to prevent to prevent resonances from damaging the satellite, we use what we call limit channels. So limiting or notching, another name for limiting, is an accelerometer or any sensor that measures a resonance. And in the control software, you assign that particular sensor a profile. So you can see here, this looks like a control profile, except there's no lower tolerance. This is what we call a limit profile. And if that sensor ever crosses your green limit profile, it'll start lowering the drive of the shaker to make sure that you never get above that green profile. So few things about limit channels. Most limiting algorithms in the industry are reactive, meaning that once you detect your limit channel goes above its tolerance, then it starts lowering the drive, how hard it's driving the shaker. One thing that data physics worked on for the safety system was a predictive limiting algorithm, which uses a pretest prediction, a self-check prediction before you start the sine sweep from a low-level random excitation, and predicts when we're going to need to limit, and we proactively start limiting, and we're able to lower any overshoot and preemptively start limiting the drive, how hard we're driving the shaker. Another advantage of the data physics limiting system is you can use math channels, which are calculated channels for limiting. So if you've got some force sensors and you want to load cells and you want to calculate the sum of 4 or 5 different sensors. Maybe you've got your test article strapped to a shaker and you've got it interfaced at 5 different places, bolted down at 5 places, and you've got a force sensor in between at each connection. In software, you can sum those and use the total net force as a limit channel. You can also, multiplication or integration, differentiation. These are all math functionality in our software. So you can do things like compute overturning moments and use an overturning moment computed from an accelerometer as a limiting channel. And the key to limit channels is, from the controller standpoint, is the speed of the control loop. And I'll talk about this a little bit later. But basically, you want the controller to be the most responsive, fastest controller as you can have. And that'll improve the performance of the control and of the limiting algorithms. So limiting, it's a critical part of making sure damage isn't done to the satellite. I've got a little screenshot here. This is, you can see the top plot is the control plot. The middle plot is the drive plot, how hard we were driving the shaker. And you can see in these bands that are highlighted, these are where one of the limit channels exceeded its limit profile. So you can see when the system is limiting, the control does drop below the reference, obviously, because you start lowering how hard you're driving the shaker. And once that limit channel no longer exceeds its reference, then we start raising the drive to the control profile again. So now I'm going to talk a little about the vibration controller considerations, what factors there are, what factors you need to consider when choosing a vibration controller. Now, this is a little bit different than your average test lab when they're deciding on a vibration controller, because everything in this, when you're testing high-value test articles, everything's about risk mitigation. So you can see a sample test system set up here. You've got the host PC, a block diagram here. You've got the host PC, which is the operator, and that's connected to the vibration controller, usually over an Ethernet connection. The vibration controller sends out a drive signal to the shaker, shown in blue here. The shaker and amplifier and test article have accelerometers mounted on them that are keying back into the controller that provide your feedback. And then you've also got an emergency stop switch that is typically in the operator room or at various locations, coming back into the vibration controller to signal it during any abort condition to the VIBE controller. So the next few slides, I'm going to focus on this block diagram and show how what considerations you need to take when you're thinking about your vibration controller. So the first part, this is going to get a little bit into the design of the controller. So the first critical, the first thing of importance you need to consider is, where are your control computations performed? Your VIBE controller, is it just a box that measures your input sensors, then relays that data over the Ethernet to your PC, and does the PC do your control correction, and then tell the VIBE controller, hey, you need to drive the shaker with 5 volts or 4 volts? Is that how the control loop works? Or does the vibe controller actually do all the computations on the controller itself and drive the shaker all on its own while communicating to the PC through the Ethernet just to, for the operator just to view the data live as the test is going? Obviously, there's downsides to the PC doing all the computations. If the PC goes offline, there's a lot of unpredictable. If you're running a Windows PC, there's a lot of things out of your control. Ethernet connection, again, there's variables there that are out of your control. You don't want any of those possibly failing during a test and causing the shaker drive to abruptly stop. So first consideration of the vibe controller is you need to make sure all control corrections are done on the controller itself, and the PC is just for data viewing and not a part of the critical data path. The second thing similar to that is the emergency stops. You've got a stop switch that is near the operator. You've got other triggers, other systems that can trigger a stop, the vibe controller to stop. Do those external stop triggers have to be routed through Ethernet to the PC, and does the PC have the stop logic that would tell the controller to stop? Obviously, that's a bad design. You want all that logic to be built into the controller itself, so there's no delay or no possible loss of Ethernet, loss of PC wouldn't cause any of the stop switches to be ignored. The other big disadvantage of running the control on the PC itself is there's going to be a latency anytime you've got an Ethernet connection. Ethernet, TCP IP is a very standardized technology. It's used throughout the vibe control industry and throughout the world, throughout all industries. And it's a great standard, but there are uncontrollable latencies that are inherent to the technology, particularly with Windows, when you're running a Windows PC. So you don't want any of those latencies to be a part of your control loop. You don't want any possibility of failure of the Ethernet or PC to cause your control loop to go down or your abort trigger to not be detected. So third consideration of the vibe controller is the latency of the control loop. And that basically means how long does the controller take to react to a change in control level, or to a limit channel exceeding its limit profile, or to the stop switch being pushed. And this is a pretty, there's no easy way, there's no one size fits all test. You can't ask a particular technical question to a controller manufacturer and get a straightforward answer, because there's a lot of things that affect this. The data path, obviously, if you're going over a network to a PC, that will negatively affect this. The speed of the processors that are processing the data, what algorithms they use to process the data, down to the hardware buffer lengths, that there's a million things that affect this. And there's no easy way to characterize, there's no one technical spec that a controller manufacturer can give to characterize this. So typically, my bottom bullet point here, the easiest way to evaluate a controller's control loop latency is to put it through a test. Test your controller against, put a very resonant test article on a shaker and set it to be a control or a limit channel, and see how well the controller controls through it. Putting different controllers through the standardized test is really the only way to get a good idea of how the controller's latency, how big or how bad or how good the controller latency is. So at Data Physics, we obviously have optimized all of our controllers for control performance. We've got lots of features and settings that we've added in for specifically to improve and maximize our controller performance, minimize the latency. Obviously, all computations are performed on the controller itself. All abort conditions are detected by the vibe controller itself, and shutdowns are quickly initiated. And everything in the controller is optimized to make sure that data errors, control loop, control out of tolerances are all detected as fast as possible. All right, so now I'm going to jump into the vibration test system that was developed by Data Physics and Team Corporation. This was the system that was used at NASA Goddard to prevent damage to the James Webb Space Telescope when it was undergoing test. The video I showed earlier. So this system wasn't just. I'm a controller guy presenting this to you, but this wasn't just the controller feature that we added. It was a feature of the controller, feature of the amplifier, feature of the hydraulic guidance. It was everything that was designed to work together in order to prevent any catastrophic damage from happening to the test article. So this safety system, we call it the soft shutdown functionality or soft shutdown feature. It prevents the shaker from producing unexpected transients during unpredictable events, things like the host PC crashing, or a full power loss to your shaker's amplifiers, or a full power loss to your hydraulic pressures. These kind of events, they typically cause a shaker to abruptly stop. So if you're in the middle of a sine wave, the drive will just drop to zero, and that causes a huge shock through your test article and can cause a lot of damage to a fragile device like a satellite. So this safety system really encompasses all of the things you can think of that can possibly fail, things that are out of our control that could fail, and protects the test article against those failures. So one example of that, example of such a failure, this data isn't from a satellite, obviously, but it's from a lightly damped test article that was mounted on a shaker. And on the left-hand side, we just killed the power to the shaker. So you can see the drive that was going to the shaker. You know, it was a sinusoidal drive, and then all of a sudden, boom, it drops to zero, and that's that. Now you can see on the top left plot at the armature of the shaker, you know, we've got our sinusoidal response, and right when the drive drops to zero, we see a huge transient, and then nothing on the armature. And then the response accelerometers at the bottom are mounted on the lightly damped resonance, and you can see how much damage and how much ringing out that kind of transient caused into the test article. So this is the kind of situation we always want to avoid when we've got a valuable test article on the shaker, and that's the kind of situation that this system prevents. On the right-hand side, we have the same failure happening with our soft shutdown system. So the system is designed so when we get a power failure of the amplifier, we're still able to ramp down everything in a controlled manner. So you can see the sine, the drive shaker is still able to ramp down. There's no transients, no damage caused to the test article. So I'm going to go through this safety system and show, you know, just exactly what how we improved each component of the system in order to guarantee that we'd never have a failure like that. So just another block diagram here. We've got the host PC provided, you know, running on 120 volt power. The vibration controller also running on 120 volt power. The shaker and amplifier running on 480 volt power, and then the slip table guidance, hydraulic guidance running on 480 volt power. The accelerometers from the shaker and test article are also keyed into a measurement system. And so everything is designed to work together to prevent any transients from coming into from being shot through the test article. So the overall system architecture of the safety system is that the vibration controller sends out a relay starting with the vibe controller going into the amplifier. The amplifier is also receiving a health status from the slip table and the guidance, from the slip table and hydraulic guidance. Then that relay goes from the shaker amplifier down to the measurement system, and the measurement system has the ability to trip the relay. From the measurement system, it goes to the physical stop switch that's in the operator room, and then from the stop switch, it goes back into the controller. So this voltage signal going out from the controller can be tripped by the shaker amplifier, the measurement system, or the stop switch in the operator. So each subsystem here was modified so that it can, one, trip this signal to tell the signal to the controller that it needs to stop. And each subsystem was also modified so that after it trips that signal, it's still able to run for another half a second to give the controller time to ramp down the test and prevent any shock. So the modifications that were made to the vibration controller, the first thing is the stop switch, which typically you have a red emergency stop switch that you connect directly to the controller. That same stop switch was used to relay through all the subsystems, and we modified that so that anytime any of the subsystems triggered that relay, we'd trigger a controlled ramp down. The other modification to that stop switch was typically we use a normally open stop switch. That's obviously not desired here, because if you have a power failure on one of your substructures on the amplifier or on the measurement system, if there's a power failure, you want that power failure to be detected by the controller. So we switched it to use a normally open or a normally closed relay. So if power failure on any of the subsystems, it'll go from closed to open, and it'll signal the controller to stop. So it's inherently safe from failure of any component. We improved the latency of the stop switch trigger by minimizing its data path. We separated it out from the control computation. So even if a stop switch gets triggered in the middle of a control computation, we can still trigger a ramp down even if that control computation is still in progress. We moved the shutdown mechanism. So once we detect a shutdown from the abort, from that abort trigger, we move the shutdown mechanism to happen at the lowest level possible. And it's actually on the DSP that's on the signal processor that's on the board that drives the shaker. So we immediately will shut down the task before the host PC even knows anything has happened. And then the last item was we run the controller through a universal power supply. So any power failure from 120 volt from the power supply would not cause the controller to stop. So the modifications made to the amplifier and shaker system, as well as the slip table and guidance system. So typically, if an amplifier, when you've got all these interlocks on your amplifier, and so all of the safety interlocks on the amplifier were modified so that if any of them trip, it would trigger the abort relay, right? So this abort relay coming in from the controller, if any interlocks trip, we open up that relay and signal the controller to stop. Now, the biggest change here is any interlock, over travel, over test, over temperature, any of those interlocks, when they do trip on the amplifier, typically the amplifier immediately shuts down. That, was that ringing out, that'll cause that ringing out, a transient, like I showed in a few slides ago. We obviously want to avoid that. So the amplifier was modified so that when any interlock trips, it does not abruptly cut the power to the shaker. Instead, the field going to the shaker is gradually shut off, which gives the controller time to ramp down. And since we are shutting the field off gradually, it does prevent any excessive force from also being exerted after the interlock is tripped. So the other modification made to the amplifier is that, or I guess to the amplifier and shaker system, is that there's a health monitor on the 480 volt power supply. So if the 480 volt power supply gets cut or interrupted, it again will trigger the abort relay and signal the controller to shut down. The last couple changes were that, if you lose 480 volt power, you've lost power to your amplifier. How can you guarantee that you're gonna not abruptly shut the test down? Well, the amplifier was fitted with extra capacitors to give it that extra energy to operate for another half second after it loses 480 volt power. So even if you lose power, the shaker can still run for another half second without any issues. And similarly, on the hydraulic guidance systems, they were fitted with extra pressure to extra accumulators to allow for the system to work, the guidance system to work in the case of a loss of power. So we also, the stop switch relay trigger is also fitted through the measurement system. So the measurement system can be connected to hundreds or even thousands of channels, measurement channels, and you can run any type of vibration detection algorithms on your measurement system, and if you detect certain events, you can trigger your vibration controller to stop as well. So one feature data physics analyzer systems have is we have the ability during our sine data reduction, which is the typical monitoring a sine test, the analyzer tests, not a vibration control, but when you're running a vibration controller, you want to monitor that data. You use a sine reduction system, and we have the ability to trigger a low latency abort. You can define your abort tolerances in our sine reduction system, and you can trigger that abort based on any channel exceeding its limits. You can also trigger an abort based on a transient event or based on if you can set an absolute threshold, say if you ever see more than 10 Gs, even if it's for a split second, trigger the controller to abort. So the complete system, soft shutdown system, incorporating the controller, the amplifier, the hydraulics as shown here. We start with the vibration controller, sends the drive signal out to the amplifier, which drives the shaker. The test article responds. You've got vibration control limit channels going, feeding back into the vibration controller. You've got measurement signals feeding into the measurement system. So that's your standard setup. Now the safety system, you've got the amplifier feeding data into the table health system, which just aggregates all of your signals, all of your health signals. You've got shaker health signals coming from the shaker, from the slip table, from the hydraulics, and any trip from the amplifier, shaker, slip table, hydraulics would immediately, or the measurement system would immediately shut down, signal that relay to shut down the vibe controller. And since each of these components has been modified so that it can run for an extra half a second under any condition, including loss of power, the vibe controller has time to completely shut down the test under any of these failures. So the final test of this system, obviously before they put a satellite on the system, NASA wanted to test this out, and so their final test that they ran was, running a sine sweep while the controller is running to just cut the power to the amplifier. They just turned off the power supply to the amplifier, the 480 volt power, while a sine sweep was running. And so you can see the top plot is what the controller did. So it got cut off, and within a short period of time, the controller had ramped down the test. The response acceleration at the armature, shows no sign of a transient, and the voltage on the armature, excuse me, it follows the same pattern. Successful ramp down, even though with an abrupt, unpredicted cut off of the power. So that concludes my presentation. It's I hope it's been informative. The safety system was developed for, I mentioned before, developed for the James Webb Space Telescope testing, but the technology has obviously all been developed by us, and we're ready to put it into production at other labs that are testing valuable test articles. All right, with that, I'll pass it back to Ryan.
Thanks so much, Raman. I'll leave it open here for a couple minutes to see what questions we may or may not have, and feel free to send them in the chat, and we'll field those as they come in. Well, I don't see much coming in on the chat line. One thing I will point out is that I did include 2 handouts that you should be able to download inside the webinar. One is an article specifically speaking to the safety system, and an article that was provided by Data Physics, so you can go ahead and download that. And also included a Data Physics resource on how to choose a shaker, just as a couple resources for you to use for specifying your vibration test systems. And with that, I'm going to conclude this webinar. Feel free to reach out to any of us as the data physics team and the representatives here at Vic Myers Associates. We'd be happy to help. Thanks so much for attending, and we'll talk to you soon.